Hello everybody, welcome to this short course on quantum computing. In the previous lecture, we had introduced the concept of spin quantization in electrons. We had also shown that prior measurement, the quantum state of a system is in a superposition of two eigenspin states. However, post-measurement, the state was seen to collapse into one of the possible eigenspin states in a probabilistic nature. We had also shown that repeated measurement along different directions leads to a loss of quantum state information. Now, as you can see, as we go on diving deeper and deeper into the quantum domain, a lot of things become counterintuitive, a lot of things become very abstract in nature. So to make our life easier, we need to make use of some kind of tool, some kind of mathematical abstraction, which we call a Hilbert space. Now let's see what a Hilbert space is. So any quantum state psi, this is basically a ket notation. I will explain later on why this is what this is actually. For the timing, just consider this to be a vector. So any quantum state can be visualized as a vector in a vector space called Hilbert space. So basically, this Hilbert space is nothing but a normalized vector space, which is linear and complex in nature. In other words, being normalized means any vector that can be defined in the Hilbert space has normalized magnitude, unit magnitude, right? And every vector follows the law of homogeneity and superposition. That's why it is a linear vector space. So let us understand this using this two-dimensional vector space, which is a complex vector space. Now, there are two basis states of this vector space, ket0 and ket1. And any quantum state ket psi is a linear superposition of the basis states 0 and 1. The C0 and C1 are the weighted coefficients, which are basically complex in nature. And since these coefficients are complex in nature, this Hilbert space is a complex vector space. Right? Now, to make things intuitively clear, we had taken into consideration a two-dimensional vector space. Now, what we need to ask ourselves is that, what is the physical significance of Hilbert space dimension? Because theoretically, we can have an infinitely long, like there is infinite dimension Hilbert space. Then what basically is the physical significance of Hilbert space dimension? So basically, the dimension of Hilbert space is equal to the number of possible outcomes of the experiment. Let us understand this again by considering our electron spin case. So basically, there is a electron with an arbitrary magnetic moment with a arbitrary spin direction given by this red arrow. Now, when it passes through a Stern-Gerlach equipment, which is measuring in the vertical direction, the state collapses either to the upspin or downspin. Right? Now, there are two possible outcomes of the experiment. So, spin up, the outcome of this thing being spin up, let us represent this by a ket0. And the outcome of this being spin down, let us represent this by a ket1. So these ket0 and ket1 are the two possible outcome vectors. That's why we consider them to be the basis state of the Hilbert space we're considering. And the initial state of the vector or of the electron spin prior measurement was in a superposition of these two states. And these two coefficients that you see, C0 and C1, they are complex in nature, and the square of their magnitude actually gives you the probability that the spin state post measurement collapses to 0 or collapses to 1. These ket0 and ket1 are more or less analogous to what you have in classical systems with bit 0, bit 1. Although physically these two things are totally different, but you can consider this to be an analogy, right? So this is about Hilbert space. Now, since we're dealing with two-level systems, and we will be dealing with two-level energy systems later on when we talk about superconducting qubits, we will only consider and will be only needing to understand two-dimensional Hilbert spaces. Right? So let us continue and let us now understand what are these ket zeros and ket 1. These are basically column vectors and normal column vectors, normalized column vectors. Right? These are called kets as per direct notation. Now the dual of kets are basically bras, which are basically row vectors that we can take by taking the transpose of the ket and taking a conjugate of that. And since this is consisting of real elements, that's why the conjugate part is not very evident over here. It's only the transpose that makes any difference over here. So these are kets and bras. So this is a dual correspondence of kets. Now coming to the inner product, a bracket notation, which is a row of 0, a row of state 0 and column of state 1, or bra of state 0 and bra of state 0 are basically multiplied. So row into column, you get one element, single number, that is a 1. Similarly, for inner product of states 1, 1, the result is 1. So what you can say is that since the inner product is 1, these are normalized. So the basis states are normalized. Now if we take the inner product of these two different states, 0 and 1 and 1 and 0, this should be a 1 over here. Just pardon my mistake. This should be a 1 and this should be a 0. So the outcome comes out to be 0. Right? So they are normalized. At the same time, they are orthogonal to each other. They are orthonormal basis states. And these orthonormal basis states forms the skeleton of the two-dimensional Hilbert space we're talking about. And any state vector can be represented uniquely using Hilbert space. Now finally coming to the whole state of the system, which is superposition weak. So when you take the inner product, you can work this out. I would like you to try this out on your own. So basically this is the expression you get. So the inner product of 0 and 0 is 1. Inner product of 1 and 1 is 1. So that you have is the magnitude of C0 square plus magnitude of C1 square is equal to 1. This means the probability is conserved. The probability of the state collapsing to 0 plus the probability of state collapsing to 1 is equal to, when you take the summation, equal to 1. So this is the conservation of probability. So whatever we have discussed in this lecture is basically very important. And I hope you'll take some time to think on this before moving on to the next lecture. I want to request you to kind of understand this properly. And there are other contents available. If you need a little bit more elaborate description, in case you need that, and you're interested, you can go for that. But apart from that, I think you'll be good. So with this much knowledge, what we will do next is that since we're one step ahead of what we had, where we had started initially, one step ahead of understanding what quantum computing is. In the next lecture or so, we will discuss a few postulates of quantum mechanics that will be essential in our case. Right? So I want to thank you very much for watching. Have a good day. So see you in the next lecture. Thank you.